We're going to be talking about the Apollo guidance computer on a much more deeper level than you might be expecting. We're going to be getting down into the details of the system. Originally, this talk was going to be a quick 1-hour overview of the entire systems. That was kind of a bold idea. And so what we've decided to do is break it down into 2 sections. For those who are the computer freaks, okay. My dear friend Michael Steele is going to be doing systems architecture, also a lot of the operating system that was run on the Apollo guidance computer. I'm going to be doing guidance and navigation. Yes, I'm going to teach you how to land on the moon, too. We had Michael up here, another Michael, who did a marvelous demonstration, and now you're going to know a little bit more of the details. He kind of stole my thunder. I have to live with that. But anyway, I'm Frank O'Brien. I'm a NASA Solar System Ambassador out of JPL. And one of the great things, now this is a different kind of role than you might be thinking of. It's all volunteer. There's about 900 of us all across the country. Yes, we walk amongst you. We might be going out with your daughters. We don't know this. And it's all pure volunteer. Your tax dollars don't pay for a thing. I don't get paid. I had to pick up the tab for this trip. But we do this out of the goodness of the heart to help spread the NASA mission, and because you're never going to be able to get an astronaut for your kid's birthday party. In a lot of ways, we're the public face of NASA in the community. And especially with the Apollo 50th, I've been doing a lecture almost every other day for the last month or 2, and it's a huge thrill, and we're just tickled to be here. So, again, we have a terribly packed schedule, so I won't sit and drone on. I'd like to introduce my good friend Michael, and he's going to be taking us through the lower level part of the AGC. After that, we're going to have a quick 10-minute break so everyone can run to the boys and girls rooms, and then we're going to pick up. So, Michael, please.
Hello, can everyone hear me? Good? Okay. So my name is Michael Steele. This is the first part about the Apollo guidance computer. First, I'll do a quick introduction what all this is about. The Apollo guidance computer, the AGC, is a digital computer that was designed from scratch specifically for the Apollo moon missions, for use on board of the Apollo spacecraft to support the landings, the moon landings between 1969 and 72. Developed at MIT between 1961 and 66, a total of 57 AGCs were built at a cost of about $200,000 each. The base clock is about 1 megahertz. All data is 15 bits. There are 2 kilowords of RAM and 36 kilowords of ROM. It's about the size of a large suitcase, weighs about 26 kilograms, and consumes 55 watts. Its user interface is a numeric display and keyboard. Some historical context. In the mid-1960s, you couldn't just take an off-the-shelf computer and put it into a spacecraft. The first mini-computers were the size of a small fridge, too heavy, too power-hungry, and too slow for real-time scientific calculations. Multiplications per second is what counts. The industry had come a long way since the previous decade. But already 10 years later, microcomputers with highly integrated circuits started outclassing the AGC hardware in many regards. There are many reasons that make the AGC especially interesting. The architecture is very 1960s and feels very alien to us today. The hardware was very innovative for its time. It has some very interesting and unusual peripherals. Its operating system was revolutionary for its time. And the mission software has all the bits to, with the right hardware attached, fly you to the moon. In the Apollo program, the final so-called Block 2 AGC hardware was used in one unmanned test mission, where it was remote controlled from the ground. 4 manned test missions. And in the 7 landing missions. Astronauts hated the idea of giving up any control to a computer. They wanted to be in charge. And while as a fallback, most of the mission could also be flown manually, the mission planners got their way. To understand the purpose and the responsibilities of the Apollo guidance computer, we need to first look at the Apollo mission. There will be a lot more in this in Frank's talk later after this one. The core strategy of the Apollo program was that instead of landing a complete spacecraft on the moon, for which an extremely large rocket would have been required, to only land a much smaller lunar lander, while the larger part with the fuel for the way back stays in moon orbit. So the Apollo spacecraft can be separated into the lunar module, the command module, and the service module. The Saturn V rocket launches it and the 3 astronauts from Cape Kennedy into Earth orbit. By accelerating at the right time, the translunar injection moves the spacecraft into a so-called free return orbit. By just coasting, it would travel around the moon and back to Earth. Right at the beginning of this 3-day journey, the command and service module extracts the lunar module and docks with it. By braking on the far side of the moon, the spacecraft enters lunar orbit. And after the 2 astronauts have climbed into the lunar module and after undocking, the lunar module brakes. This is called powered descent. And lands. After taking off again, the lunar module rendezvous with the command and service module. The 2 astronauts from the lunar module climb into the command module, and the lunar module is jettisoned. The remaining command and service module accelerates at the far side of the moon for a trajectory towards Earth. For entry, only the command module remains. These excellent visualizations are from Jared Owen's How the Apollo Spacecraft Works videos, which I highly recommend. The command and service module and the lunar module each contained 1 Apollo guidance computer. It was the same hardware, but attached to partially different I/O devices and with the software adapted for the specific spacecraft. The astronauts interact with them through the display and keyboard units, which are mounted alongside these hundreds of switches. The computer's responsibilities during the mission are to track the position and speed, the state vector, of both spacecraft, stabilize the spacecraft's attitude, calculate and control engine burns, and monitor or control the Saturn V during launch. In order to understand how the Apollo guidance computer does all of this, we'll look at its architecture, the hardware implementation, some of its interesting peripherals, the system software, and in Frank's talk after this one, the mission software. The architecture of the AGC CPU can be described as a von Neumann accumulator machine with 15-bit ones complement big Endian arithmetic. So we will talk about the instruction set, the arithmetic model and instruction encoding, as well as the memory model, I/O operations and counters, and finally the interrupt model. Machine code instruction sets vary widely. The instruction set of a modern ARM processor, which is mainly optimized for runtime performance, consists of about 400 instructions. Sublec is a language mostly of academic interest that shows that a single instruction can be enough to solve the same problems as all other Turing-complete languages. While a more complex instruction set can achieve higher code density and contribute to higher code performance, it also generally means that the CPU will be drastically more complex. A computer from the early 1960s consisted of only a few thousand transistors as opposed to today's billions, which is why this is the sweet spot for the AGC. 36 instructions provided just about the performance that was required for the mission. These are the 36 instructions. Some load and store instructions, arithmetic and logic, control flow instructions, I/O instructions, and instructions for dealing with interrupts. The memory model is the cornerstone of the instruction set. Memory consists of 4,096 cells, numbered hexadecimal 000 through FFF. Each cell contains a 15-word, a number between 0 and 7 FFF. Almost all changes to data in memory go through the 15-bit accumulator, also called the A register. A program can copy words between the accumulator and a memory cell, but also add, subtract, multiply, and divide values as they're moved around. The data in memory can have many meanings depending on how it's interpreted. These values may represent integers, while those 3 words are meant to be decoded as machine code instructions. Code and data in a single address space make the AGC a so-called Van Neumann machine. The CPU's program counter PC always holds the address of the instruction to be executed next. The load instruction copies the contents of a given memory cell into the accumulator. Then the PC goes to the next instruction. The add instruction adds the contents of a given memory cell to the accumulator. And the store instruction copies the value in the accumulator into memory at a given location. The generalized versions of these instructions we just saw use K as a placeholder for a memory address as an argument. These cards are a quick reference for of instructions. This is the generic syntax of the instruction, a short description, the exact operations in pseudocode. This one takes memory address K and adds it to A, the accumulator, the encoding of the instruction in memory, and the number of clock cycles. What do I mean with original syntax? If you know any modern assembly language, the original syntax, that is the name the original designers gave to instruction, will feel very foreign and confusing. For this talk, I'm using my own syntax, a more modern syntax, to make it easier to explain the CPU both to people with and without a background in machine programming. In Frank's book, and of course in all original documentation, you will find the original syntax. Let's have a look at the instruction set in detail. Here's an example of the load instruction. Load A, indirect 200. On the left, you see the set of registers of the AGC. Most operations work with the accumulator, so we will be ignoring the other registers for now. When executing this instruction, the CPU looks up memory at location 200, reads its contents, and copies it back into the accumulator. This is the store instruction, load indirect 200, A. Like with all instructions, the first argument is the destination memory, the second one the source, the accumulator. It looks up address 200 in memory and copies the contents of the accumulator into that cell. There's also an exchange instruction, which can atomically swap the contents of the accumulator and a memory cell. The add instruction will look up the contents of a given memory address, add it to the contents of the accumulator, and store the result back into the accumulator. And there's the subtract instruction. It takes the contents of the memory address, subtracts it from the contents of the accumulator, and stores the result back into the accumulator. The result of subtraction can be negative, so we need to talk about how negative numbers are expressed on the AGC. To make things easier, let's just look at 4-bit numbers. 4-bit unsigned integers can express values from 0 to 15. With sign and value encoding, the uppermost bit corresponds to the sign, and the remaining 3 bits represent the absolute value. Consequently, there are 2 separate values for +0 and -0. This encoding is hard to work with since 0 transitions need to be special cased. One's complement has the order of the negative numbers reversed. 0 transitions are simpler now, but there are still 2 representations of 0. Modern 2's complement encoding has only a single encoding for 0 and is fully backwards compatible with unsigned addition and subtraction. In the 1960s, computers designed for scientific calculations were usually 1's complement, and so is the AGC. Let's go into detail how to do math with 1's complement. Unsigned 4-bit numbers can express values from 0 to 15. In 1's complement, these values, the values 0 through 7, match the unsigned values 0 through 7, and the negative side is organized like this. Unlike 2's complement, the 2 sides are perfectly symmetrical. So negating a number is as easy as complementing it, that is, flipping all the bits. The 2 representations of 0 are +0 with all 0 bits and -0 with all 1 bits. Addition in the positive space is equivalent to the unsigned version. Same in the negative space when mapping signed negative numbers to their unsigned counterparts. It gets interesting when we have a 0 transition. Signed 6 minus 4 is 6 plus -4, which is unsigned 6 plus 11, which in modulus 16 is 1. We have a carry. In 1's complement, a carry needs to be added to the end result, so we get 2, which is the correct result of 6 minus 4. The trick to jump over the duplicate 0 on a 0 transition by adding the carry is called the end-around carry. An overflow means that the signed result does not fit into the number space. Signed 7 plus 1 would result in signed -7, which is incorrect. The same happens when overshooting negative numbers. After applying the end-around carry, the result of signed 7, in this case, is incorrect. The CPU detects this and flags the result. The accumulator has an extra bit to record the information about the overflow. We will call it V. So if we have code that reads the value of 7FFF from memory and adds 1, the result is 0 and an overflow is detected, so the accumulator is flagged. The store instruction, in addition to writing A to memory, does extra work if there's an overflow condition. It clears the overflow condition, writes +1 or -1 into A, depending on whether it is a positive or a negative overflow, and skips one instruction. This way, the program can detect an overflow and use the +1 or -1 to apply the signed carry to a higher order word. By storing A to memory, we now have the double word result. In one's complement, negating a number is as easy as flipping every bit in a word, so there's a dedicated instruction for loading and negating a value. LDC, which stands for load complement, reads a word from memory, negates it by inverting all the bits, and writes it into the accumulator. Incrementing, that is adding 1 to a word, is such a common operation that there is a dedicated instruction that increments a word in memory in place. There's no corresponding decrement instruction. Instead, there are two similar instructions, augment and diminish. The increment instruction adds 1 to the original value. The augment instruction adds 1 to all positive values and subtracts 1 from all negative values. It effectively increments the absolute value, retaining the sign. And the diminish instruction decrements positive values and increments negative values. Optimized for scientific calculations, the CPU has dedicated multiplication circuitry. The mul instruction reads a word from memory and multiplies it with the accumulator. When you multiply two signed 15-bit words, you'll need up to 29 bits. That is 2 words for the result. The complete result will be written into 2 registers, the upper half into A and the lower half into B. B is a separate 15-bit register, which is mostly used together with the accumulator with instructions that deal with 30-bit data. Double word values are expressed with the uppermost bits in A, or if in memory, at lower addresses, and the lower bits in B or at higher addresses, making the AGC a big Indian machine. Assuming the normalized form with matching signs, the effective value is the concatenation of the 2 times 15 bits of the values. Division also works with double words. It takes the combination of the A and B registers as a dividend and a word from memory as the divisor. There are 2 results, the integer result and the remainder. The result is written into A and the remainder into B. Some other instructions also allow using A and B as a double word register. Load A, comma, indirect 200 looks up address 200 in memory and reads the words at this and the next cell into A and B. The load complement variant does the same, but inverts all bits during the load. There's no instruction to store A and B in a single step, but there's a double word exchange instruction. And finally, there's an add instruction that works in double words. And to load and store just the B register, there's an exchange instruction for that. For working with tables, there's the indexed addressing mode. Any instruction that takes an address as an argument can use it. In this example, load A, indirect 00 plus indirect 80 first looks up the value at address 080, which is 2, adds it to the base 700, which results in 702, reads from that address, and writes the result into A. What does this mean? There's a table in memory at 700. In the example, it contains multiples of 3, and an index into the table is stored in memory at 080, which in this example is 2. So we read the entry at index 2 of the table, which is 6. Without a base address, we get the syntax in this example. Load A, double indirect 80. The base is effectively 0 in this case. The CPU will look up the value at 080 in memory, add it to the base of 0, so it's still the same value, and reads from that address. In this use case, memory at 080 effectively stores what C programmers know as a pointer, and 3A0 is the pointer's destination. The instruction performed an indirect read. By default, instructions are executed sequentially. The program counter PC increments as instructions are executed, always pointing to the next instruction. Control flow instructions like jump and conditional jump change that. When the CPU hits a jump instruction, it will load its argument into the program counter, which means that execution will continue at that address. JZ, jump if 0, only jumps if A is 0. Otherwise, it continues with the next instruction. Similarly, JLEZ only jumps if A is negative or 0. CCS, count, compare, and skip, is a 4-way fork for execution. Depending on whether the value in memory is positive, negative, plus 0, or minus 0, it will jump to one of the next 4 instructions. If you know the value is positive or 0, you can ignore the other 2 cases and just fill the first 2 slots. And if it's supposed to be only negative, you have to skip the first 2 slots. They should never be reached, but it's good practice to fill them with error handlers. Since CCS also puts the absolute diminished value of the memory location into A, the special case of CCSA can be used for loops that count down A. The call instruction is meant for calling subroutines, aka functions. It is like a jump instruction, but it saves its origin, so the callee can return to it later. For the call instruction, the program count is incremented first and then copied into the link register, LR. Finally, the argument of the call instruction is copied into the program counter so that execution continues there. The link register now contains the return address. At the end of a subroutine, the ret instruction effectively copies the contents of the link register into the program counter, so execution resumes just after the call instruction. If the subroutine wants to call its own subroutine, the program has to save the link register before and restore it afterwards. There's an exchange instruction specifically for this. For additional levels, a stack can be constructed using the indexing syntax. So far, we've seen the following registers. The A register is used for memory access and all arithmetic. It is combined with the B register for double with arithmetic. The program counter keeps track of what to execute. And the link register remembers the return address when calling a subroutine. What we haven't seen yet is the 0 register. It always contains 0, so if we read from it, we get 0, and when we write to it, the value gets discarded. There are 3 more registers that we'll talk about later. The 8 registers are numbered. That is, they're assigned memory addresses. This means that the first 8 words in memory are actually occupied by the registers, and they can be accessed using their addresses in all instructions that take a memory address. This allows for much greater flexibility in the instruction set. We can load A with the contents of the B register by reading the contents of memory at location 1 into A. The constant of 0 can be loaded into A by just reading from memory at 7, which is the 0 register. A can be incremented by incrementing memory at 0, and B can be used as a pointer by reading from double indirect 1. Let's look at the memory map more closely. Memory is 4096 words and goes from 000 to FFF. The registers are located at the very bottom of memory. Including these, there are 1024 words of RAM, random access memory, and 3K words of ROM, read-only memory. The AGC was originally architected to only have this little RAM and ROM, but there's actually more. Let's look at the RAM area. The uppermost quarter is banked. This quarter is a window through which one of 8 different banks can be accessed, each 256 words in size. The erasable bank register, EB, points to one of these banks. If EB is 0, bank 0 is visible in the banked area. If EB is 5, bank 5 is visible. Addresses in the fixed area always represent the same RAM cells, but these are not additional cells, but the same as banks 0 and 1. This means that there is a total of 8 times 256 words of RAM, 2 kilowords. ROM is organized similarly. The lower kiloword is banked. The fixed bank register FB selects one of the 32 banks. Support for more than 32 kilowords of ROM was added in the last minute. The super bank bit can switch the uppermost 8 banks to a second set, so a total of 40 kilowords are supported by the architecture. The fixed ROM area will always show the same contents as 2 of the ROM banks. The designers chose banks 2 and 3 to simplify address decoding. In practice, fixed ROM contains core operating system core and fixed RAM core operating system data that have to be available at all times. The remaining functionality is distributed across the different ROM and RAM banks. Switching the RAM bank can be done by writing to the EB register. This is not a separate instruction, but can be expressed by writing A to memory location 3. If A is 5, writing A to EB will make RAM bank 5 visible in the banked RAM window at 300. The same store instruction could be used to write to the FB register in memory location 4 to switch the ROM bank, but that wouldn't work for the common case. If code in one bank wants to call code in another bank by first switching the ROM bank, load FB, and then doing the function call, writing the bank number into FB will switch out the bank the code is currently running on, so it won't be able to execute the call instruction. Instead, it will continue using some completely unrelated code that happens to be at the same address on the other bank. To call code on a different bank, the FB and PC registers have to be changed atomically. Call F is a synonym for the existing double word exchange instruction. The code first has to load the bank and the program counter into A and B, which call F then atomically moves into FB and PC. The exact same exchange AB, indirect for instruction can be used for a far return. It moves the original values back into FB and PC. The two bank registers only hold 5 and 3 bits respectively. The other bits are 0. There's a third bank register, BB, both banks, which mirrors the information from both other bank registers. The call far both banks synonym is a double word exchange instruction that updates the program counter and both banks. Subroutines usually have their private variables on particular RAM banks. Call for both banks passes control to a function on a different ROM bank and also directly switches the RAM bank so that the callee can immediately access its variables. Return for both banks returns to the caller, restoring its RAM bank configuration. The unusual ordering of the bank registers was chosen to allow for a double word exchange of FB and PC, as well as for a double word exchange of PC and BB. Now we've seen all 8 registers. There are 8 more special locations in memory above the registers, the shadow area, which we'll talk about later. And above those, there are 4 so-called editing registers, which make up for the missing shift and rotate instructions. An editing register will apply a logical operation to any value stored into it. When writing a 15-bit value into the raw editing register, it will be moved to the right by 1 bit, and the lowest bit will be cycled to the top. The result can then be read back. ROL rotates left. SHR shifts to the right, duplicating the top bit. And SHR7 shifts to the right by 7 bits, filling the top with 0. This is needed for the interpreter system software component that we'll talk about later. We have seen that the CPU is connected to RAM and ROM, the memory bus. But computers also talk to peripheral devices, that's the I/O bus. We've already seen the address space for memory. There's a second address space to talk to devices. There are 512 I/O channels, numbered 000 through FFF. Each channel is 15 bits, and the in and out instructions can read words from and write words to I/O channels. For many devices, a channel contains 15 individual control bits. A control bit can, for example, toggle a lamp on a display. The out or instruction sets individual bits, and out and clears bits. So I/O instructions can work on the whole word or do Boolean operations on them, and, or, and XOR. To make the Boolean operations also usable between registers, channels 1 and 2 are aliased to the B and LR registers, which allows for instructions like AND A, B or A, B XOR A, B. For AND, there's also a dedicated instruction that works on A in memory. So after the registers, the shadow area, in the editing registers, there's another special area, the counters. Like I/O channels, they connect to external devices, but they don't send bits or whole words back and forth. Instead, they are controlled by hardware pulses or cause hardware pulses. On every pulse, time 1 gets incremented, for example, while other counters take the number stored into them by code and count down, generating pulses. When I/O devices need to signal the CPU, they can interrupt normal execution. Next to the program counter, which points to the next instruction, there is the instruction register, which holds the current opcode. When an interrupt happens, the CPU copies PC into a special memory location PC prime and IR into IR prime, and then jumps to a magic location depending on the type of interrupt. In this example, 814. When the interrupt handler is finished servicing the device, whoops. No, go back. When the interrupt handler is finished servicing the device, the IRET instruction will copy PC prime and IR prime back into PC and IR, so execution will continue at the original location. Memory locations 8 through hex F are shadows of the 8 registers. PC and IR are automatically saved by interrupts, and the remaining registers need to be saved by software if necessary. The overflow and condition flags cannot be saved or restored. So while there's an overflow condition, until the next store instruction, which resolves the overflow, interrupts are automatically disabled. The 11 interrupt handlers have to reside at the start of fixed ROM at 800. There are 4 words for each entry. Typical interrupt code, entry code saves A and B, loads A and B with a bank and PC of the actual handler, and jumps there. Interrupt 0 is special. It's the entry point on reset. Next to the interrupt return instruction, there's an instruction to cause an interrupt in software and instructions to enable and disable interrupts. There's one more special memory location. At hex 37, the Watchdog. This location needs to be read from or written to at last every 0.64 seconds. Otherwise, the hardware will decide the system software is unresponsive and cause a reset. We've now seen the instruction set, and in the examples we have seen the codes that represent instructions in memory. Let's look how the encoding works. For this load instruction, the upper 3 bits are the opcode representing the load A, and the remaining 12 bits are the address. This allows for a total of 8 instructions, but there are more than 8 instructions. RAM addresses always start with 00, uppermost 2 bits, and ROM addresses start with anything but 00, and this can be used in the encoding. So the store instruction, which only makes sense on RAM, only needs to encode 10 address bits instead of 12. Which makes room for another 3 RAM-only instructions. The same is true for the increment instruction, which makes room for 3 more, as well as CCS, which shares an opcode with jump, which only works on ROM addresses. Since jumps to the bank register don't make sense, these codes are used to encode STI, CLI, and extend. Extend is a prefix. It changes the meaning of the opcode of the next instruction, allowing for this second set of 2-word instructions. There's one more special call instruction called to, which is called LR, the link register, which is the return instruction. But this one is not a special case. Instead, return is a side effect of calling memory location 2. Call 2 will continue execution at location 2 in RAM. Location 2 is the same as the link register, in this case 0421, representing the return address of 0421. So it executes this address as if it were an instruction. All addresses that start with 3 0 bits, so all addresses start with 3 0 bits, so this is a call instruction to this exact location. So effectively, control would be transferred to the return address. Index addressing is achieved by using the index prefix. An index instruction consists of 2 instruction words, index and the base instruction. The address encoded in the base instruction is the base address, and the index instruction encodes the address of the index. Index is an actual instruction. The CPU reads from a given address, 080 in this example, then adds its value, 3, to the instruction code of the following instruction, 3700, which is stored in the internal IR register. It then uses the resulting instruction code, 3703, for the next instruction, which is load from 703, the effective address. If an interrupt occurs after the index instruction, that is no problem, because IR contains the effective instruction code, which will be saved into IR prime and restored at the end of the interrupt handler. Finally, there's one index encoding with a special meaning. When the address looks like it's referencing a shadow instruction register, it's an interrupt return instruction. Looking at the instruction set architecture as a whole, there are many quirky and unusual features when compared to modern architectures. It uses 1's complement encoding instead of 2's complement. It has no status register. The overflow flag cannot be saved, so interrupts are disabled until overflow is resolved. The store instruction may skip a word under certain circumstances. The CCS instruction can skip several words and can be outright dangerous if the instruction following it uses prefixes. There are no shift or rotate instructions, but magic memory locations that shift and rotate when writing into them. Most Boolean instructions only work on I/O channels. Indexing is done by hacking the following instruction code. And the architecture has no concept of a stack. Indexing has to be used if one is needed. This was the architecture of the Apollo guidance computer. Next, let's look at how this architecture is implemented in hardware. The hardware implementation runs at 1 MHz, is microcoded, and uses integrated circuits, core memory and core rope memory. We'll look at the block diagram and how instructions are implemented by microcode, and then about how the schematics map to integrated circuits on modules in trays. This simplified block diagram shows the AGC at the hardware level. Each box contains on the order of 500 logic gates. The dotted lines are wires that move a single bit of information, and the solid lines are 15 wires that move a data word. These units deal with timing and control, and these are the central units. The central register unit stores A, B, LR, and PC, and the arithmetic unit can add and subtract numbers. And the memory components deal with RAM and ROM. The main clock of about 1 megahertz feeds into the sequence generator, which keeps cycling through 12 stages, which is one memory cycle, MCT, memory cycle time. Instructions usually take as many memory cycles as they need memory accesses. So load, add, and store take 2 cycles, and jump takes 1. The sequence generator contains a collection of 12-step microprograms for each MCT of each instruction, like this one for the load instruction. In each step, the entries send control pulses to the other units, which are connected through the write bus. The control signal RA, for example, instructs the register unit to put the contents of A onto the write bus, and WA makes it write the value on the bus into A. Memory is also connected to the write bus. WS will copy the bus contents in the memory into the memory address register, and RG and WG will read and write the G register, which buffers the cell's value after a read and before a write. So in stage 7 of the load instruction, for example, RG puts the memory buffer onto the bus, and WB writes the memory bus contents into the temporary B register. And then at T10, a B gets put on the bus and it gets written into the A register. At the beginning of every memory cycle, the hardware sends the memory address S, usually what's encoded in the instruction, to memory, and copies the contents of that address into G. In the second half of the MCT, it stores G back into the same cell. So if we show memory timing next to the microcode, as well as the pseudocode version of the load instruction, we can see it loads the value from memory into G, copies it into B, and copies B into A. More interesting is the exchange instruction. It saves A into B, reads from memory into G, copies the result into A, copies the old value into G, and stores G into memory. Division, for example, takes several MCT, and its microprogram is way more complex. But there are more microprograms than the ones for the machine instructions. Since there's only a single add-in unit in the whole computer, incrementing and decrementing is done by converting the pulses into special instructions that get injected into the instruction stream. There are 14 of these so-called unprogrammed sequences with their own microprograms. Some count or shift, some are for interacting with debugging hardware, and these control the interrupt and reset sequences. The complete schematics are publicly available and fit on just 49 sheets. The whole implementation uses a single type of gate, a 3-input NOR gate. 2 of these are contained in one integrated circuit, and about 100 of these ICs form a logic module. 24 logic modules and some interface and power supply modules are connected together in tray A, which also contains the I/O and debug connectors. Tray B contains various driver and amplifier modules, as well as RAM and ROM. RAM is implemented as magnetic core memory, which stores bits in magnetized toroids. Reading a bit clears it, so the memory sequencer makes sure to always write the value again after reading it. Without masterage like tape, the AGC has an unusually high amount of ROM. Core rope memory encodes bits by wires that either go through or past a ferrite core. The 500,000 bits per computer were woven completely by hand. Trays A and B are put together like this and hermetically sealed, making for a rather compact computer. This is the orientation when installed in the spacecraft, with the 6 ROM modules accessible, so they could in theory be replaced during the mission. And that was the hardware part. Next, let's look at the devices connected to the computer. We will look at the core devices that allow the AGC to maintain the state vector, some quite special devices that you don't see on many other computers, and the peripherals used for communication with astronauts and mission control. The gyroscope is the core peripheral that the AGC was originally built around. The AGC rotates it into a certain base position with a CDU-CMD counters, and then the gyro detects rotation around the 3 axes of the spacecraft that can be read from the CDU counters. Using the gyroscope, the spacecraft always knows its attitude, which is its orientation in space. The accelerometer measures acceleration forces on the 3 axes. The 3 values can be read from the Piper counters. So far, it's just like an iPhone. But the optics and command module does not. Cannot find that one in an iPhone. On the command module, the optics are used to measure the relative position to celestial objects. The computer uses the opt CMD counters to move the objects to point toward the general direction of a star, and will read in the astronauts fine-tuning through the opt counters. The landing radar sits at the bottom of the Lunar module and measures the distance to the ground. The radar interrupt will be triggered whenever a new measurement is available, and the RN-RAD counter contains the new value. The Lunar module's rendezvous radar measures the distance of the command and service module during rendezvous. After setting the 2 angles in the CDU-T and CDU-S counters to point it towards the other spacecraft, it will automatically track it and cause radar interrupts when new data is available, which can be read from the RN-RAD counters. The command module, the service module, and the Lunar module all contain reaction control system, RCET jets, that emit small bursts for holding or changing the attitude. On the Lunar module, there's 1 bit for each of the 16 jets. Setting a bit to 1 will make the jet fire. The system software uses a dedicated timer, time 6, and its interrupt, T6RUPT, for timing the pulses. The user interface is provided by the so-called DISKEY, which stands for Display and Keyboard. It has 19 keys, 15 lamps, and several numeric output lines. Keys generate the KeyRupt interrupt, and the key number can be read from the key-in I/O channel. The numeric display is driven by the out-O channel. There's bidirectional digital radio communication, S-band, between mission control and each spacecraft at a selectable speed of 1.9 or 51 kilobits per second. Data words from mission control are shifted into the in-link counter and trigger interrupt uprupt. Data words to be sent are stored to the I/O channel DNTM1, and the downrupt interrupt will signal a program when it can load the register with the next word. These were some of the interesting peripherals. The AGC's system software makes it a priority-based, cooperative, but also preemptive, real-time, interactive, fault-tolerant computer with virtual machine support. The topics we'll talk about are multitasking, the interpreter, device drivers, and the so-called waitlist, as well as the user interface and mechanisms for fault recovery. The AGC has many things to do. It does mathematical calculations that can take several seconds, and it does I/O with its devices. It services interrupts when the device wants the computer's attention. A simple example would be a key press on the DISKEY. It does regular servicing of devices, like updating the display, and it supports real-time control, like flashing a lamp or firing boosters at exactly the right time. There's only a single CPU, so it must switch between the different tasks. Batch processing multitasking computers work on long-running jobs, one after the other. But if some jobs have higher priorities, it makes sense to run a job for only, say, 20 milliseconds, then check the job queue and keep running the highest priority job in the queue until it terminates and it is removed from the queue. Then keep picking the highest priority job. The jobs have to manually check at least every 20 milliseconds whether there is a higher priority job in the queue by doing a so-called yield, which makes the AGC a priority, scheduled, cooperative multitasking computer. A job is described by a 12-word data structure in memory that contains the PC and both banks register that point to where the job will start or continue running, as well as a word with a disabled flag in the sign bit and a 5-bit priority. The so-called core set consists of 7 job entries. -0 in the priority words means the entry is empty. Job 0 is always the currently running one. When a new job gets created with a higher priority, the yield operation will exchange the 12 words, so the new job is job 0. Negating the priority will put a job to sleep, so yield won't switch to it again. Negating it again will wake it up. The first 8 words in the job entry can be used for local storage for the job. Since it's always job 0 that is running, these words are always conveniently located at the same addresses in memory. The executive is a set of subroutines that control the job data structures. You can create a new job pointed to by a pair of PC and BB registers of a given priority, change the priority of the current job, put the current job to sleep, wake up a given job, and terminate the current job. Yield is not an executive function, but a two-instruction sequence that checks the new job variable, in which the executive always holds the ID of the highest priority job. If job 0 is the highest priority job, there's nothing to do. If there is a higher priority job, it calls the change job subroutine, which switches to that job. New job isn't just a variable in memory, but it's also the watchdog word. So if it isn't accessed regularly, that is, cooperative multitasking is stuck, the hardware will automatically reset itself. A lot of the code on the AGC does scientific calculations. Calculating, for example, just the sum of two products of a scalar and a vector would require hundreds of instructions in AGC machine code. There is library code that provides all kinds of operations on single, double, or triple precision fixed point values, vectors, and matrices. It also provides a software multi-purpose accumulator, MPAC, which can hold a double, triple, or a vector, depending on the mode flag. In C-like pseudocode, we would, for this example, load the vector into the MPAC, multiply it with a scalar, save it, do the other multiplication, and add the result to the saved value. Formulas like this one need to store intermediate results, so a 38-word stack is provided. If a job uses math code, the MPAC, the mode field, and the stack pointer will be stored in the remaining fields of its core set entry. The stack will be part of a data structure called the VAC, which will be pointed to by the core set entry. A job can be created with or without a VAC, depending on which subroutine it's created with. The machine code version of the example code would still be very verbose, which is why many function calls passing pointers. The designers of the AGC software designed to create a new and compact language that will be interpreted at runtime, a virtual machine. The interpretive language is Turing complete, and in addition to the MPAC, has 2 index registers, 2 step registers, and its own link register. The encoding manages to fit 2 7-bit opcodes into one word, which allows for 128 opcodes, and explains why there is a specific shift right by 7 function in the CPU. The 2 operands are stored in the following 2 words, allowing 14-bit addresses. 14-bit addresses means interpretive code doesn't have to work with this complicated memory layout anymore. It allows addressing about half of the ROM at the same time. At the lowest kiloword of each half, RAM is visible. So interpretive code can pick between one of these 2 layouts. This is the complete instruction set of the interpreter. Regular machine code and interpretive code can be mixed and matched inside of a job. The exit instruction will continue executing regular machine code at the next address, and call intpret will similarly switch to interpreter mode. In addition to long-running math tasks, the system software also supports device drivers. When a device needs the computer's attention, for example, in case of a disky key press, it causes an interrupt. The current job will be interrupted, and the interrupt handler will read the device data and return as quickly as possible. If there's more to do, it can schedule a job for later. Some devices need to be serviced regularly. A 120 millisecond timer causes interrupts that read data from and write data to certain devices. The numeric display of the disky, for example, only allows updating a few digits at a time, so its driver is triggered by the 120 millisecond timer. The timer interrupt cycles through 8 phases, which distributes the device driver across time to minimize the duration of one interrupt handler. Some devices need to be driven at exact times. If, for example, a job decides that it needs to flash a lamp twice, it would turn it on immediately and then schedule 3 waitlist tasks in the future at specific times. The first one will turn the lamp off, the second one will turn it on again, and the third one will turn it off again. The sorted time deltas of the waitlist tasks are stored in the data structure LST1, with the first entry always currently counting down in a timer register. And LST2 contains a pair of PC and BB for each task. These are the subroutines to create a new task and end the current task. The timer that controls the waitlist has a granularity of 10 milliseconds. Other timers can fire at the same rate, but are offset. And the work triggered by them is designed to be short enough to never overlap with the next potential timer-triggered work. This is complicated by device interrupts, which can come in at any time. The duration of an interrupt handler causes latency, and the maximum duration will reduce the allowed time for the timer handlers. The core system software makes no guarantees about the timing. It's up to all the components to cooperate so that the real-time goal can be met. The Pinball Program is the shell of the AGC. Key press interrupts schedule a job that collects the digits for the command and updates an in-memory representation of what should be on the display. The 120 millisecond timer triggers the display update code. When a command is complete, Pinball will schedule a new job. Mission control has a remote shell in form of a disk key connected through the S-band radio. System software that supports human life has to be able to communicate malfunctions and be able to recover from them. The alarm subroutine takes the following word from an instruction stream, displays it, and illuminates the prog light. This should be interpreted as a warning or an error message. The AGC is full of validity and plausibility checks that help to find bugs during development and helps better understand potential issues during the mission. Some kinds of failures triggered by various hardware watchdogs or by code make it impossible for normal operations to continue. In addition to showing the error code, they also cause a hardware reset. But the system software offers recovery services. A job can have a recovery code for its different phases. During execution, it sets the respective phase, and if an abort happens in any job or task, the currently separate recovery routine gets executed, which could, for example, clean up and try the work again, skip to a different phase, or cancel the job altogether. The phase change code call sets the current phase for a job in the recovery table, for example, phase 5 for job 4. Each phase is associated with a descriptor of a task or a job with or without a VAC. So during normal execution with several jobs and tasks scheduled, if an abort happens, the core set and wait list are cleared, and the contents of the recovery table are activated. Scheduling tasks and jobs for all jobs that set up recovery code. Some types of failure, like corrupted memory, are not recoverable. They cause a fresh start, meaning a full initialization of the system without running any recovery code. And that was the AGC system software, which concludes part 1. I would like to thank everyone who helped with this talk. This includes the indirect contributors who wrote the books, the original documentation, the websites, and the software. Thank you very much for your attention. We will continue now with Frank O'Brien's talk on the role of the AGC in the Apollo missions.
Well, thank you very much. We're going to take a quick break here, and I'm going to continue on with a talk about guidance and navigation. It's actually going to be kind of funny, or it may be a little bit fun, and also of some of the mission programs that are being used. It's a very different style, totally different change up. Well, hopefully to see you there. Time to run to the boys' room or girls' rooms or whatever, and I guess we'll meet up in 10 minutes. Well, welcome again. Hope everyone's gotten to have a little bit of a break. Again, I'm Frank O'Brien. We're going to be talking a little bit about the Apollo guidance computer. It's a little bit of an interest of mine. Wrote a few words on it. Way too much fun. We're going to have a little bit different talk right now. We're going to be talking about guidance navigation. How do you fly to the moon? This is one of those great questions. And then we're going to talk about landing on the moon and the mission programs. With the gent that was doing the demonstrations, by the time you leave, you're going to be able to do it yourself, I promise you. You know, you always worry about what happens if the pilot dies. You got that. You're going to have it all figured out. I promise that tonight. Anyway, I have a small thing. We're going to be tight on time. Save all the questions till later. But if you do have, one of the nasty problems is man of a certain age, way too much rock and roll and flying too much without a headset. If you have to ask anything, it's just tough for me to hear. So if we could do work with that, that'll be fine. But right now, I got to get one of my pet peeves out of the way. Okay, I write about the Apollo guidance computer. I talk about it. I really get incensed at the idea that someone's going to say, my watch is more powerful than the Apollo guidance computer. My microwave beats the pants off of it. And we won't even talk about my calculator, right? Well, how do you define computer power? Now, we're at a Vintage Computer Festival. The idea is that we're kind of celebrating machines which aren't exactly, crazy supercomputers. So think of it. How do you define power? Real quick, anyone? Memory. Okay, what else? Again, too much rock and roll. Okay, speed. All right, I'll tell you a story. I got a little Honda Fit. I could do 85 miles an hour on that. Was certified by the local law enforcement. Cost me a few $100s for that certification. Get about 40 miles a gallon. The vehicle that lifts up the Saturn V and takes it to the launch pad goes only about 1 mile an hour. Its mileage is measured in feet per gallon. Which one's more powerful? Right? Which one's more powerful? I don't know. It's not going to clock 85 on the Jersey Turnpike. So, we have a real paradigm shift here that we're working with. We're talking about a computer. Yeah, 2K of ROM. Okay, anything here probably beats the pants off of that. 36K of RAM. I'm sorry, ROM. That's all your software. You had no disk, no tape. You had nothing like that. So, okay, all those things, maybe my calculator does beat the pants off of it. But here's a silly little thing. Measuring computer power is more than just simply how fast the CPU is, just like my Honda, just like the Corolla Transporter. You can't make that kind of equation, or you just can't make that kind of equality between the two. What we are all celebrating here in computers is the idea of systems that will process data and do multiple things. God knows how many Internet of Things ideas we've had already come up. Think of it. I've got a little computer that has 2K of RAM. 36K total programming, runs 5 virtual machines. All that implemented in 36K. How good is your code? Think hard before you answer. Oh, by the way, in that 36K, you have to get from the Earth to the moon, land on the moon, ascend from the moon, and then come back home. Want to talk about your code again? Think hard. So, a computer, even an old laptop like mine, everything in there is designed to get data in, out, get a little bit processed. Apollo Guide's computer handled maybe about 150 different devices. This just tells the time. Which is more powerful? This has got 50 years on the AGC. Think hard before you start making quick, easy, oh, my calculator stuff. So anyway, I got that out of the way. I feel much better. We won't go there. Anyway, so getting to the moon is a tough job, especially when you're talking about all this being designed about 55, pushing 60 years ago. Remember, all that preliminary work had to be done ahead of time. We had to do all of this autonomously. I'm a man of a certain age. I grew up in the Cold War. My dad was a fighter pilot for 20-something years. He strapped on a nuclear weapon, went looking for Russians. That was his job. Some people are plumbers. Some people are programmers. My dad straps on nuclear weapons. Makes for an interesting childhood. We were terrified that the Russians were going to be jamming our signals. Therefore, we had to do this autonomously. You had to take all those computers in mission control, pack them into a little box, and you can see the box over here at our auctions. Pack it all into that. This is with, again, mid-1960s technology. We had to have it accurate within fractions of miles. Yeah, you're going 250,000 miles. If you went 60 miles off course, that's the difference between a perfect orbit or smacking into the moon. We got it down to feet. Accuracy was generally measured in 500 to 800 foot. Think of that. That's pretty good. 1960s technology. How powerful is your computer? A digital autopilot, completely brand new concept. We're all familiar, airplanes have autopilots. These were all analog. These were all, yes, vacuum tubes, resistors, transistors, a few other things, but it was all analog. The concept of a digital fly-by-wire system did not exist. The only time we got it into an airplane, guess what they used? An Apollo guidance computer. That was the very first digital aircraft, an F-8, flown out at Edwards Air Force Base. That's pretty clever. We had to get off the Earth, into lunar orbit, rendezvous, entry, all with this one computer. And again, no secondary devices, no tape. Certainly, if you can imagine what the disks were in 1960s, they weighed about 2 tons, was about that big. You're not going to be able to make it there. And now all that recovery and reliability, you could not fail. We didn't go into, Michael didn't go into a lot of the options for all of our recovery options. We're not going to do that either. We could talk that offline. But the key thing is, you can't let a silly thing like a system crash keep you from getting to the moon. That's just not an option, right? When we had those system failures, first off, and again, this is a topic for way offline because it gets way down to the weeds, but no, the computer was not at fault. No, Buzz Aldrin didn't put a switch in the wrong position. The explanation is long, convoluted, and not appropriate here, but computer did just what it was supposed to do. It did not reboot. You hear the word restart. It did not reboot. What happens when you reboot? Oh, everything goes away, right? Well, you're landing on the moon. You don't want to lose all your data. How good is your code? Think of it. So anyway, we have the three main components. Computer, the AGC, like the one you'll see over here, is pretty much blind, deaf, and dumb. No different than if you just pulled a processor chip out of your PC right now. It doesn't know squat. It doesn't know how to interact with anything. The things that are important for the AGC to interact with are two things. It needs to have some orientation information. Remember, we're flying through space. We need to know which way is up, right? And how do we do that? Brilliant technique, using optics. We used all this stuff back in the 60s. We use it today. Those three components are all part of guidance, navigation, and control, all the way from the earlier days of Gemini to the spacecraft we're launching today. And when we go to Mars, we'll be using them all exactly the same. This is the DISCI, display and keyboard. This is a marvelous device. This is one of my favorites. Think of it. Early 1960s, no concept of interactive computing, right? My idea of interactive computing was sitting down late at night with way too many coffees and a tasty cake, typing on punch cards, feeding them into a hopper. That was my interaction. But now you can imagine what it would look like with astronauts pulling 8Gs, trying to punch. No, it's not going to work. The imagery is just too bad. So we had to invent an interactive language, for lack of a better phrase. And it turns out it's the exact same language we use today that I use on this, you use on all of your computers, so you can thank these guys for it. Pizzas. What the heck does pizzas have to do with this? Well, if I'm a guy or a gal, I'm from the New York area, or I'm from Wisconsin, but I live in New Jersey. New York is a city of restaurants, lots of tourists. If you came to the States, came to New York, and was hungry but didn't speak a whole lot of English, what are you going to say? You find a cop in the street, you go, eat, eat. Well, yeah, someone's going to figure out you're hungry. But, you know, New York's a city of restaurants, right? What do you want to eat? Well, pizza. Eat pizza. My English teacher back in grammar school would freak out if she heard me say that. But it's enough to get the idea across. Eat pizza. Not grammatically sophisticated, but it's all I need. It's a verb. It's a noun. And then you ask yourself, well, how does this all play in? Take a look at those keys over on the left. The two primary keys on the Apollo computer are verb and noun. That's how you interact. A verb is something we have as an action. A noun is what we want to act on. So eat what? Pizza. Everything has a numeric code. Okay, verb 6, or 16, we display data. Well, what data? How about the time your engine's going to fire? Useful information in a spacecraft. Very, very cool. And if you think that that's, oh, very clever, very nice, now I know how to fly to the moon, and it is. It's all you need to know to run the DISCI. Think of this. We use it today. And you go, no, I have a Mac, or I have Linux, or I have a Windows machine. You use this exact same syntax when you say print, taxes, edit, email. We use this today, verb, noun. Think of it. So anyway, again, I was a pilot. One of the things when you fly aircraft is that it's absolutely important to have the important instruments in front of you. You don't really care about the temperature in the back of the plane, you know, as being your central instrument. That is irrelevant to your airspeed, altitude, where you're going, that sort of thing. And if you take a look, the disky is square in the center of the pilot and the commander and the command pilot's field of view. Your attitude information and that crazy scrolly looking thing is for all of your reentry data. Those are the most important instruments that you'll find in the spacecraft. In the lunar module, weight was everything, so they even threw out the seats. You figure you're a big enough boy, you can stand on the moon. After all, you're going to the moon. You can put up with it. And so the instruments that are at eye level, and we'll look at this in a minute, attitude, altitude, all the rest. The computer is a beautiful thing. It's right at waist level. I don't know how many musicians are in here, but I think it's science fiction that someone can play the piano and not look at the keys and be able to carry on a conversation. I think that's fantasy. Here, you didn't even bother looking. Your fingers knew just where to go. Dave Scott, Apollo 15, had the phrase, again, it was like paying, you know, your fingers had all the memory. Your fingers knew where to go. So now we got the computer out of the way, the disky, and all the rest. We got to figure out which way is up. We have this inertial measurement unit. Michael talked about it. It's what we call a stable platform. It's about that big. It has mutually perpendicular gyroscopes. It holds it fixed in space. The spacecraft rotates around it. It's a beautiful piece of mechanical engineering, easily the most precise piece of equipment in all of Apollo. Also, accelerometers. It can't measure velocity, but it can measure accelerations. We just take it, we just get the derivative, figure it out over time, boom, we have velocity. Very cool. And yes, you got to have the beauty shot, right? We can go ooh and ah, and boy, that's a clever piece of equipment. Anyway, the other thing, the other interface that the computer uses is to look outside. And these are the optics. And yes, it's a sextant and a 1-power telescope. Big running joke is only the government can be talked into buying a 1-power telescope. But it was really pretty much a spotting scope. And the whole idea of this, again, the computer is blind, deaf, and dumb. It has no idea where it is unless it can have some piece of equipment tell it where it is. And this is what the optics are all about. We will take that information, combine it with the software, and figure out our position, velocity, and all the rest. So how do you do this? I was real lucky a couple months ago. If you're ever, I don't know if there's any such thing here on the West Coast, but on the East Coast, there's a school, and I just finished it, that you can take in celestial navigation. And it's a beautiful thing. That sextant would be recognized by a mariner 200 years ago. A 200-year-old sextant would be able to be recognized by a mariner today. They work the same. It is a timeless, beautiful instrument. So timeless that the exact same principles, no different, are used in the Apollo spacecraft for taking sightings on stars. It's a timeless instrument. Hundreds of years, and there is no reason to change it. Beautiful device. And on the Apollo spacecraft, this is the command module. Here we have Al Warden working on doing his star sightings. Now, what do you get out of all those fancy star sightings? Here are the only questions. Yes, there's going to probably be a quiz on this, but think of it. What do you need to know to do guidance and navigation from the Earth to the Moon or to Mars or wherever else? 3 questions. You answer those 3 questions, apply a little bit of math, and the world works for you very, very nicely. Right? Anyone got the answers on? We're going to start. This is supposed to be a learning case. Which way is up? That way, right? Any dissenters? Any comments? This way's up, right? Again, too much rock and roll. Well, let's elaborate on this. If I'm at the North Pole, standing up, which way is up? Right? I got a buddy at the South Pole. Which way is up to him? Looks a lot like this, right? In space, they kind of go like this, right? So we can't say in a gravity field which way is up, can we? Houston, we have a little problem here. Which way is up? Dear friend of mine lives in Scotland. His pointing up looks a heck of a lot different than one out here. Which way is up? Any last questions? Because I don't want to run late. It's any way you want. Think of it. It's in space. I can have up going this way. I can go up going this way, that way. It doesn't matter. But the key thing is, through all of this, is that you have to have everyone agree. We have to have a standard coordinate system that we all agree on. It doesn't matter where it starts or where it's pointing, but as long as we all agree, it's just like having the prime meridian. It could have gone anywhere. We've decided it goes through Greenwich, England, and that's fine enough for everyone, and everyone agrees. So, now we have to figure out how we do that. You wondered what these things were for, right? Yeah. Okay. Like I said, you're supposed to learn something today. You're going to learn how to navigate by the stars in space. I get that fancy-dancy sextant. I pull it out. I have to figure out, with two stars that are at random positions in the sky, I have to have that and define a three-dimensional framework for me to be navigating to the moon with. First, I need to know which way is up. Well, I do my first sighting. I got to use two stars for this. And I don't know, we'll say the speaker over here is that star. Oh, this is you. This is a star. $5 at Michael's craft shop. These things work real well. I take a sighting on a star. Okay? Is that locked in some frame that doesn't move? Well, I look here. Okay, those are pretty locked, but I can still rotate. I need to lock up all my degrees of freedom with two sightings. And so now I take a second sighting. And we'll say it's over there by the bathrooms. Well, that's really good, but what happens if I want up to be this way? Neither one of these stars are pointing toward it, right? All right. Here's where you have to pull out your high school geometry. You don't need fancy, well, the math gets a little complicated in real life, but these are the principles. Pull out your high school geometry. Think of it. I've got sightings on two stars. That establishes a plane. Yeah, we have to pull out that high school geometry stuff. If I have a plane, I can figure out a perpendicular to it. Something normal to that plane. Remember, I'm pointing here and I'm pointing, I guess that's the bathrooms. I've now got three axes to play with. But none of them are really useful. I now have one for the plane here. I now have a second plane, and I have all three axes perfectly defined like this in space. Very, very clever. But now you go, no, I want up to be this way, and none of these are pointing to that. Okay, now we pull out our high school trig. You don't have to be, the biggest lie is that NASA is super, super smart, nobody can understand it. You're already 3/4 of the way there. All we do, and we do this a lot in graphics cards, believe it or not, we do a transformation, a little matrix rotation, and now if I want up to be like this, it's just a little matrix by matrix, poof, poof, poof. Now I have established my orientation in space. I now know which way is up. Where am I? I don't want to run late. I'm going to be using that same sextant not to measure my position amongst the stars, which really isn't going to change on a flight to the moon. I need to measure it by the angle between a star and the moon. Simple trig. Simple trig. Oh, it's done in 3 dimensions, and it does get a little bit more complex, but we know that. But the next big question is, where am I going? It's nice to know which way's up and where I am, but which way am I headed? Am I headed to the moon? Am I headed right on course? Is it turning out to be a bad day at work and I'm not going to make it that day? No landing on the moon today? How do I do that? Well, we know which way's up. We know where we are. That fancy platform and that beauty shot tells me exactly how fast I'm going. And it turns out we navigate in space the same way you do on Earth. Dead reckoning. Think of it. It's what, I don't know exactly, it's what, maybe 45, 50 miles to San Francisco? You're going 45 miles an hour, except on the 101 during rush hour. Yeah. You're going 45 miles an hour. You can figure out it's going to take you about an hour to get to San Francisco. Oh, okay, fine. We use and have used, especially in the days before a lot of radio navigation and a lot of the GPS stuff, we did dead reckoning navigation in aviation for dozens and dozens of years. Today, you still have to demonstrate your proficiency. You can't use GPS as a crutch. So how do you do that? Well, this is the area which I used to fly in. I flew out of Princeton Airport in Jersey. If I wanted to go to Morristown, it was about 45 miles. I had a little plane, so it only went about 90, 95. So yeah, you can kind of figure out. It'll take me about 30 minutes. Now, in aviation, like the sextant, we had a wonderful tool. It's still used today. Yeah, kids, I know a lot of the younger folk like to use a calculator. I'm old school. This is called an E6B. This was invented in the 30s. And with it, I can calculate my time, speed, distance. There's a little thing on the back to figure out my wind corrections. It is a beautiful, timeless instrument. Not even all that expensive. It's just a circular slide rule with a few extra scales. It's a beautiful, timeless thing, and it allows us to navigate dead reckoning anywhere in the United States, anywhere in the world. This is such a timeless device, like the sextant, which has been around for hundreds of years. This has been around for hundreds of years. I have proof. It's a bold statement. I have proof that this device was used in the 23rd century. That's a bold claim. I have photographic proof that this wonderful device to do all my calculations of flight was in the 23rd century. Proof. Right? Right there, yeah. 23rd century, another timeless instrument like the sextant. Proof, it turns out that's actually Gene Roddenberry. You know, of course, he flew in the Second War. Gene Roddenberry's E6B. I hope you're taking good notes. This will get you anywhere in the universe. Anyway, so we're going to get back to some real geeky stuff again. Pardon me. We have this servicer. This is your guidance and navigation routine. Every 2 seconds it runs. It runs probably about a fraction of that. The way the Apollo guidance computer ran its software is that it wasn't one big monolithic program. You actually fired off a little task that would run, it would start, schedule its next execution, and terminate. Very, very cool. No unnecessary things running. Just fire it up, let it run. It's already scheduled its restart time, and now we're on our way for the next one. It was 2 seconds every time it ran. That was completely fine. We weren't talking microsecond resolution, but if you ever notice, when you see pictures of guys lifting off the moon, the spacecraft's kind of wobbling on its way up. That's the 2-second routine. It goes up. It turns out the engine was never right through the center of gravity, so it was pushing it off to the side. 2 seconds later, it realizes the mistake, pushes it back over. And it just nods its way into orbit. This digital autopilot was absolutely astounding. You had to not only account for different mass properties. Think of what you have to do when you're flying an airplane or a spacecraft. Well, if I'm using thrusters, the little rocket engines, I need to know how long to fire them. That's a function of mass. If those things are getting a little bit, if you have a rather lightweight spacecraft versus a heavy one, all those control laws change. It's just exactly the same as flying an airplane. If I'm flying if my plane is a little overweight, and yes, once or twice I did, I need to move the wheel differently than if it's extremely light, just me and not much gas. The autopilot needs to know the same thing, and there's wonderful laws. We don't have time to go into it, but we can later, offline. But the beauty is you can emulate almost any vehicle with software. They took a Gulfstream jet, tweaked its autopilot, now it flies just like the space shuttle. They used it for their approach and landing tests. And again, the very first aircraft that did this used an IMU, a DSKY, and an Apollo guidance computer. You can read about it on the thing. Anyway, we're probably getting close to time here. Let me see. How much time? Oh, God, we're going to be here all day. Anyway, so Michael had that marvelous, marvelous emulator. He wasn't so bad landing, was he? I agree. He was pretty good. If you saw that, and I hope you did, perhaps a little bit of this is redundant. I apologize for that. Again, I wasn't expecting him to be such a hit here. But anyway, we go through 3 different phases to land on the moon. Each one makes a little bit of sense when you think of it in the big picture. Think of that. If you're going 5,500 feet a second, we'll say 3,600 miles an hour, what's the first thing you got to do? You got to land and it's got to be 0. So you got to slow down. Now, the most efficient way of landing is that you put the engine out, you fire it. The only problem is you're looking straight up. And you saw that with Michael's emulator. Eventually, it's time to take a look at where the heck you ended up, right? That's kind of useful if you're landing on the moon. You want to see where you're going. When I land an airplane, I'd like to know where I'd like to know at least that my runway's in front of me. And then we do the fancy stuff at the end. What Michael didn't cover is all the, we're going to say the reassurance and the information the astronauts are working with when they land. This is the schematic view of it. Again, he brought up all that stuff. You fire up the landing program, P63, about 10-15 minutes beforehand, sometimes 20. It actually does all the guidance calculations. It does take a while. So it's not like press a button that says land on the moon and everything, hops into things. We have our braking phase, and this really isn't the scale because braking is the vast bulk of the entire landing. We have our approach, where you get your first view of the landing site. And then it's time not to take manual control. That's another bug I got in my head. But we're going to do our terminal descent. We're going to do that program 66 and land. Again, I apologize. This might be redundant with what Michael had. Again, I'm just thrilled at what he had. But here's what your DSKY looks like. You have just a couple seconds before, 35 seconds, that servicer starts running. The DSKY blanks. Think of it, it's software. You can do things like that and you don't have to buy an extra light bulb. That works out pretty well. It's just an acknowledgement. You're not going to change anything, so it just blanks for 5 seconds. And then it counts down. Now, firing up the engine is well, it's kind of a commitment, isn't it? So, like all good computers, they ask, are you sure? Right? Are you really, really sure you want to do that? And the way it does it, it flashes a special verb, asking for permission. It's verb 99. Verbs actually work two ways. It's instructions for the computer. There's also a few verbs that it would like you to do. And verb 99 says, okay to go. And you just hit the button marked proceed. Again, take good notes. You don't know whenever you're going to be in this situation, the pilot's going to die. You know how they, again, every pilot I know, and yeah, me too, all sat down and, we get on a plane, and we're always desperate that they're going to say, does anyone know how to fly a plane? And you want to save the day? Well, hey, take good notes. Next time we're going to the moon, you can be all brushed up on this. So, 3 seconds to go, hit proceed. Now, you're laying on your back. You're not even all that interested in watching the stars go by. You certainly can't see the moon go by because you're facing up. And you got all those fun little numbers flying around. How do you know you're doing any good? Come on. I mean, you're landing on the moon. Okay, Houston's probably saying, yeah, you're go. Everything looks nominal. Happy, happy day. But, you're the pilot in command of that spacecraft. You want a little bit more reassurance. Just a simple word go isn't going to help you. Well, I mean, it does, certainly, yeah. How do you know things are going okay? You have a cheat sheet. Before every mission, you know what that descent's going to look like. After all, they spent lots of years trying to figure out the optimal trajectory. And so, if you go and look at just a few correctly configured lunar modules in museums, like the museum I worked at, you'll see for a landing configuration, it has a cheat sheet. And it's brilliant. The things that you're really interested in is my altitude okay? Am I going down at the appropriate speed? Not too fast, not too slow. Am I pitched over at the right attitude? All these are important questions. And yeah, it's an index card that is Velcroed to the instrument panel. It is no more complex or simple than that. What are the antenna angles? Remember, Apollo 11 had communications problems that they were surprised to get? Well, if they have it, at least they have a cross-check of where that antenna is supposed to be pointing. This is the information you need as pilot in command. How much fuel you're expected to have. If you're 5 minutes into the landing, and okay, was it 49%? 5 minutes into the landing, it's supposed to be 49%. If you only have 30%, it's going to be a bad day, and you're not going to land on the moon today. These are important things to cross-check, and it is none of these fancy little devices or instruments. It's a piece of cardboard Velcroed to the instrument panel. If you take a look at any major in any airliner, if you take a look at the launch videos of the space shuttle, you will see the cockpit covered in this stuff. Especially the space shuttle. You can't even look out the windows of the shuttle practically. I'm being silly, but it's almost that bad. For all the checklist items, all the important, I need to know this now questions. And they're just Velcroed right on up there. I kept a couple of Velcroed things on my airplane. Worked like a champ. So anyway, we're following our descent now, going from ignition, throttle down, again you saw that with Michael's stuff, to about 8 minutes, 9 minutes-ish. When it's time to bring the lunar module, let the windows look at the ground, let you get your first look at it. And remember, you only have a couple minutes. We have our approach phase. Michael made references to one of the important values. The computer has absolutely no idea what's underneath it. No idea at all. All it can tell you, and it's a useful piece of information, all it can tell you is that this is where I know I'm heading. Has no idea on Apollo 11 that it was going right into a crater. They're already 4 miles off course, 5 miles. And so you get a little number up there. And it's called the landing point designator. That's a great word. I love that word, phrase. Now, in today's technology, in today's aircraft, you have a head-up display. It's projected. Sometimes you even get them in cars. It's a beautiful technology. They didn't even have that in a fighter jet around the time the LEM was being designed. That was fantasy. That was like landing on the moon, getting a head-up display. Did not exist. You're lucky to get a little pipper to where you're going to be bombing. That was the technology at the time. And if they were to do it, it was going to probably weigh hundreds of pounds. They've already ripped out the seats. There isn't much else to rip out. You can imagine a fancy head-up display, if they could do it, would not, well, the thing would be too heavy to fly. So, all the computer is doing, since it's a rather clever little device, certainly more powerful than my wristwatch, is that it knows where it's going if nothing else changes. And so it'll display the angle. Now, here you are, you're already pitched back. It's giving you an angle. How? I'm not real good at deciding what angle I'm going to be landing at. I still don't know what angles I landed at. So, oh, I'm sorry, I jumped ahead. All that's true. This is from an exhibit I put together. I flew this lunar module when I was 15. Yeah, my life was downhill after that. This is at the Cradle of Aviation in Long Island, where we have not 1, not 2, not 3, but 4 lunar modules, because Grumman needed to empty out warehouses, and the Cradle of Aviation was right down the street. I highly recommend it. It's a fabulous thing. This is from the Lunar Module Simulator. And again, the computer did wonderful things about managing lots and lots of devices. It wasn't just thrusters and the platform and all the rest. Those fancy tape meters, all that was under control of the computer. That cross pointer, horizontal velocity, forward, back, left and right, also all by the computer. Had neat little, again, talk about simplicity when you need simplicity. There was a marvelous, marvelous little cross-check instrument about how well your engine's doing. It was the thrust to weight. And that was, again, one of the things on the cheat sheet. That wasn't computer controlled. It was just a weight on a spring and a meter. Nothing more simple or complex than that. Anything else would have cost money, time, effort, and all the rest. But you can put a little bob on a spring, and that's all it was. But this is the landing point designator. You saw in Michael's demonstration what looked like everything was painted, but you have that parallax problem. If you're a petite woman versus a tall guy, if you look at a particular angle, it's going to point somewhere different based on your height. So you have to have 2 of them. And so, here's the inside, here's the outside. You can see that they're skewed a bit. And with that, since they're skewed a bit, I have to, if I have 40 degrees as my angle, I have to line up both of them. And there they are. Only then am I comfortable with the idea that I'm going down at 40 degrees and this is where I'm headed. Final descent. Another great urban legend. I bristle at this. Boy, wasn't Neil Armstrong a great astronaut? He sat there in the middle of almost a complete failure of that landing, wrestled control out of that obnoxious computer, and like a true American hero, landed it all by himself. I mean, it makes for Hollywood, doesn't it? That was a standard part of the descent. That was the last part. More importantly, he did not take manual control. This is a fly-by-wire. Yeah, you could probably fly the LEM manually. Just like if you had to, you could probably fly an Airbus manually. No one in their right mind would want to do it unless it's an emergency. He was flying that LEM just like you fly an Airbus or a Boeing today. Yeah, he was moving the controls, Those controls aren't connected to anything except the computer. Actually, they're connected to more. That's a long story. But he was telling the computer, which has all these fancy flight control laws, exactly how to go about its landing. We're running low on time. Why don't, again, we only have a couple minutes, and I'd like to finish up without rushing. Rendezvous, probably mathematically as intense as landing, if not more so. We can go into all of these things. You design a rendezvous profile starting at the end. Where do you want to link up? What kind of lighting conditions? Lighting is everything. One of the horrible things about the airport I flew into is that every afternoon, the sun was straight down the runway. My fighter pilot dad had a great piece of advice, says, learn how to squint. Because that's the only thing you can do. So you design the lighting so that the sun is behind you. You design it for these kind of things, communications with Earth. All the other major points are worked backwards. If I have to be there at a particular time and I know how long it's going to get there, I can turn a crank. It'll tell me when I need to fire the engines. Very, very clever. We could talk all day, and unfortunately, we just don't have the time. Anyway, so we're finishing up. We can take questions afterwards if you like. This is all the fun stuff in my mind. Anyway, so one quick last little thought. Okay? My watch is pretty clever, right? We went to the moon with 1 megahertz machine and 36K of code. 2K read-write. We're running a multi-programming operating system with 5, count them 5 VMs. That's a pretty neat trick. I'd like to see an Apple I, which has, comparable speeds and all the rest, run a half dozen VMs. So how good are your systems? How powerful are they? And my watch is dying on me. But think about that. Again, I bristle at the idea that my microwave can fly you to the moon. Yeah, your phone may be more powerful, and I will make a strong argument, and I truly believe this. This is a comparable device to the Apollo computer rather than your watch or your microwave. When you think of all what this little device has to do, you line up the things side by side. Oh yeah, it has less memory and it has lots slower. It has the same constraints as this guy. And yeah, if you're really still hung up on CPU speed and memory and all the rest, and you say that this is so much more powerful, why are you spending your life on Instagram when you could be flying to the moon, right? That's it.
So before you all leave, we have 15 minutes for questions if you'd like to take questions.
Yeah. Okay, here we go. Before you guys, I love doing these talks. You get to ask questions, right? That's the way all this works, right? I do the yap, and then you ask about it. We're going to turn that on its head. Because, folks, it's trivia time. All right. Here's the trivia. There's all kinds of great things. I'll bet you don't know the answers to. Okay, Prime Contractor, the company that was legendary, famous for guidance and navigation. They did the Polaris, ICBM or IRBM. There's a computer out there. They designed that. They were the prime contractor for it, I should say. They did the inertial nav inside the submarines. They did the guidance platform for the Titan missile. Absolutely state-of-the-art, top-of-the-line, legendary. You didn't go anywhere else for your guidance platforms. What company was that? MIT designed the computer and wrote the software. Raytheon manufactured it. They were the subcontractors. Come on, be careful. Oh, Draper is now what MIT Instrumentation Lab was back then. But be careful. I'm going to start doing the Jeopardy, Final Jeopardy tune. If you any guesses? Come on.
Everyone knows this company. It's a household name. It was the AC spark plug division of General Motors, which is now Delco. AC spark plug, greatest guidance navigation systems ever built. One of their products is downstairs off to the side, the Polaris guidance system. AC spark plug, and you go to their website and they'll tell you all about it. They were the prime contractors. Okay? Who made the chips? Fairchild's a very good guess. It turns out by the time they were manufacturing flight units, and I'm thinking mostly for the flight units, Fairchild stopped making the chips. They weren't profitable. Now the chips, understand when they first designed this in 1960, they were working on a different computer that became the Apollo computer. To get just a triple input NOR was $1,000 quantity one. Try going, and that's 1960. You can do the arithmetic what it'd be today. You tell your boss, yeah, we need a handful of them. Over time, and because of, the military and NASA bought roughly 1 million of these chips. Obviously, the price came down. They bought virtually the entire United States production capacity of chips for two projects, the Minuteman missile, its guidance system, and the Apollo guidance computer. Fairchild, yes, they were the big ones. They stopped making them. Who replaced them and actually manufactured the flight chips? No, RCA, I mean, I have RCA down the street. They weren't really big in semiconductors, especially in the early 60s. Any other guesses? Come on, you're going to play Stump the Chump with me, so I get to do that with you, okay? Again, very good guess. They did a lot of preliminary stuff. No, the answer is Ford. Philco Ford. We had a Philco TV in the house around those days. Philco, one of the great chip manufacturers. Third question, there's a typo in here. Oh, I'm sorry, no, there isn't. Who made the first stage? Now we know the Saturn V rocket. There was the smaller one, the earlier one, called the Saturn I and the Saturn 1B. Who made that first stage? Not the upper stage, which was Douglas. Who made that one? Final Jeopardy music if you're not careful. No, not Boeing. Boeing did the whole Saturn V. If you look at it, after all their acquisitions, they did the entire Apollo, Saturn V and Apollo spacecraft. Who wants to guess? Who was famous in rocketry? So much so that they were asked by Werner von Braun to make the first stage of the largest rocket at the time. Again, tough to hear. Rocketdyne made the engines. It was Chrysler. The whole moral of that trivia exercise, we had GM doing the guidance platform, Ford doing semiconductor, and we have Chrysler building rockets. It's a very different world today. In the 60s, everyone was in aerospace. Think of that. So anyway, now you get to hit me. Go ahead. What do you have? Oh, questions? Come on, you put up 2 hours of this, you got to have questions. Okay then. Sir, wait, yeah, the one that's after they say goodbye. It says I got one more. Go ahead. And again, please speak up so.
What is program 65?
Okay. The descent to the moon was a number of programs, separate ones for separate phases. P-63, initial braking. P-64, approach. P-65 was completely automated landing. 66 was pilot input to the landing. If they had used P-65 on Apollo 11, they would have landed in the middle of a field of boulders at the bottom of a crater. The idea that, oh, the pilots, being, just, ego-driven and all the rest. No. If I'm landing, if I didn't have an autopilot on my plane, but if I did, and the autopilot wasn't putting me where I needed to be, you can bet I'm going to take control. And the same thing here. It saved a number of missions. And in the end, and I believe it was the last 3 missions, they actually deleted P65. Because no one was foolish enough to kill themselves and let the computer do it. And it wasn't, obviously with all this, there was a huge trust in the computer. But again, it didn't know what was below. And the pilot is in the loop. And of course, that's the way it always should be. Anything else? Yes, sir, in the back. And again, please speak up because it is noisy.
I have a microphone here.
Oh, perfect. Thank you, sir. Oh, recovering it?
Yeah, recover the first stage. It doesn't weigh much. I mean, a little bit of fuel or a
You know
parachute.
how much that stage weighs? You want to guess how much that stage weighs empty after it's all drained out of
A
fuel?
lot less than when it's full with 2 other stages on top of it.
That thing weighs in at about 450,000 pounds. That's empty. It was almost 5 million pounds with the fuel. There isn't a parachute on Earth that'll bring it down slow enough. Yeah, and you got no gas. Sir? Oh, okay, and that's a fair point, and I just slammed that together and, all right, guilty. The book's correct, but... Sir?
Could you talk a little bit about the Apollo 10 near disaster where they reset the AGC?
Yeah. Okay, Apollo 10. Not the first use of an advanced profanity-laced commentary. Apollo 10 was a dry run, did everything except the final descent to the moon. They really had to work out some important procedures for that mission. The problem you're referring to on Apollo 10, remember the lunar module splits into 2 pieces. The bottom part is the descent stage, stays on the moon, functions as a launch pad, if you will. And again, think of it. Batteries are dead. It's got landing gear and empty fuel tanks. Nothing you need to bring back up, right? So we split it into 2 pieces. In the 1960s, and it killed a countless number of people, unlike in the airlines today, they really hadn't pioneered cockpit resource management. Gene Cernan was there doing what he thought he should be doing, and he was setting switches. They were supposed to do the staging on the primary system. He knew he had to flip a switch as part of the checklist. This violates every command response checklist protocol I've ever worked with. And he went over because he knew he was going to flip a switch, and he flipped it, and it turns out he went to the abort system. They were going to test the abort system anyway. It was a checklist item, and he flipped the switch in the wrong way. So, the abort guidance system was not configured correctly to handle that. They weren't going to use it until later. But the way it was configured was that it was going to search out for the command module. That was the thing. It was going to be doing the rendezvous part, which the Eggs is an amazing machine. It really is. 4K. Now, instead of the primary computer doing a normal launch, you stage, and now it starts looking around for the command module. Last it knew it was over this way. And they started tumbling. It would not have been a good day on the moon because you wouldn't be coming home. But that's what happened. And now, cockpit resource management, I made the allusion to bad decisions in airliners. We have, unfortunately, bad history in flying years and years ago. Occasionally it still pops up, where it's like, I'm the commander of this aircraft and you're just here to, serve coffee. And that's to the first officer. I'm being silly. The idea that you have to work as a team, cross-check all of your work, was a problem we fixed in aviation going into the 70s, after there were a lot of problems like that. These guys growing up as fighter pilots never, I guess, got the word. And that's my commentary. That's not, all the rest. But it was a switch error by Gene Cernan, flipping it to the wrong guidance system, which was not configured for the that phase of the mission.
We have time for just one more question.
Okay, well, we can take this offline. Again, I only have a hard stop because I have to catch a plane home. But again, thank you so very much. I really hope you enjoyed this. It's been a lot of fun being here. And again, I have to thank Michael. He was just great with the level of detail that he brought.